Let's look at linear independence. For example, color pictures in books and magazines are often printed using the CMYK model, that stands for cyan, magenta, yellow, and black. We can create any color by printing dots with these colors. So let's C equal 1000M, the magenta color, equals 0100, Y, yellow, 0010, and K, black, 0001, represent pure cyan, pure magenta, pure yellow, and pure black. Suppose we want a color that has 10% of the cyan, 58% of the magenta, 3% of the yellow, and 20% of the black. That is, we want the color 0.1, 0.58, 0.03, 0.2. Can we express it in terms of CMYK? Yes, you bet. 0.1, 0.58, 0.03, 0.2 is just going to be 0.1 times C plus 0.58M plus 0.03Y plus 0.2K. Anything in R4, anything in four-dimensional space, can be represented as a linear combination of these four vectors, CMYK. Do we need a fifth color? Green, G equals 1010, a mix of cyan and yellow? No, because G is just C plus Y. C is 1000 and Y is 0010. So you add them together and you get G. So you don't need G. Anything we can express in terms of CMYKG can be expressed using just CMYK. The mathy way of putting it is that the span of CMYKG is the span of these vectors CMYK. Which brings us to the definition of linear independence, one of the key definitions of the course. A set of vectors is said to be linearly dependent if you can express one of the vectors as a linear combination of the others. If no vector can be written as a linear combination of the others, we say the set is linearly independent. Now, this definition works only for sets of two or more vectors. We can't apply it to a set of one vector because there is no other vector. It wouldn't make any sense to say that you can express a vector as a linear combination of the others when there are no others. Is this set linearly independent, CMYKG? No, because you can express one of the vectors as a linear combination of the others. G equals C plus Y. We saw that a moment ago. Here's the more all-encompassing definition of linear independence that works not just for sets of two or more vectors, but really sets of one or more vectors. A non-empty set of vectors S, V1, V2, blah, 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 V sub n, is linearly dependent if C1, V1 plus C2, V2 plus blah, 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 plus C sub n, V sub n equals 0 has a non-trivial solution. That is, has a solution where not all the C sub I are 0. Such a set S is linearly independent if the only solution to C1, V1 plus C2, V2 plus blah, 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 plus C sub n, V sub n equals 0 is the trivial solution. That is, where all the C sub i's are 0. For example, determine if the set 1, 2, 3, 2, 3, 4, 5, 9, 13 is linearly independent or linearly dependent. So going back to the definition, again, we want to be able to express C1v1 plus C2v2 plus C3v3 equals 0 using non-zero C1, C2, C3. You know, it's okay if one of them is 0, even two of them are 0, but they can't all be 0. Okay, we're going to call these vectors v1, v2, and v3. Let's look for solutions to c1, v1 plus c2, v2 plus c3, v3 equals 0. We know, of course, that c1 equals 0, c2 equals 0, c3 equals 0 is a solution. That's the trivial solution. We already know that. So again, we have this from the previous slide. We can write this as a matrix equation, ax equals 0. So this is our matrix A. And notice when you multiply A times this vector x, you get ax equals 0. In other words, you basically get what we have above. 1c1 plus 2c2 plus 5c3 equals 0, etc. Okay, so we have that as a matrix equation. You can express it as a system of equations like this on top. And then the augmented matrix just looks like this. We know how to solve a system of equations like that. Its reduced row echelon form is going to look like this. In other words, we get C1 plus 3C3 equals 0 and C2 plus C3 equals 0. Move the free variable C3 to the other side, and we end up with C1 equals negative 3C3, C2 equals negative C3, and C3 just plain equals C3. Okay, so if we pull out the C3, factor out the C3, we end up with C1, C2, C3 equals the vector negative 3, negative 1, 1 times C3. So there is a non-trivial solution. C2 C1v1 plus C2 v2 plus C3 v3 equals 0. Any solution C1, C2, C3 is going to work as long as it's a multiple of negative 3, negative 1, 1. So you can plug in any value for C3 here, anything from negative infinity to infinity, including 0, multiply it by this vector, and you're going to get a solution. Thus, the set v1, v2, v3 is linearly dependent because we have non-trivial solutions to this vector equation. Let's find a linear dependence relation among v1, v2, and v3. Well, we just saw a moment ago what that is. Negative 3v1 minus v2 plus v3 equals 0. That would be our linear dependence relation because we saw a moment ago that c1 equals negative 3, c2 equals negative 1, and c3 equals 1 works as a solution. And if you do plug in v1, v2, v3, you find that this does indeed equal 0, 0, 0. So we said earlier that a set of vectors is linearly dependent if you can express one of the vectors as a linear combination of the others. How does that connect to the definition we saw a moment ago, the other definition of linear independence and dependence? I'll show you. So can you express v1 in terms of v2 and v3? You bet. So we had negative 3v1 minus v2 plus v3 equals 0. If you get the v1 all by itself by moving the v2 and v3 to the other side, you end up with this. And next, divide both sides by negative 3, and you end up with v1 equals negative 1/3 v2 plus 1/3 v3. So again, as we saw a moment ago, a set of vectors is linearly dependent if you can express one of the vectors as a linear combination of the others. And indeed, here we have it. Here we have one vector as a linear combination of the other two. So that implies that the set is linearly dependent. We already knew it had to be linearly dependent. We weren't sure whether you could express v1 in terms of v2 and v3 or v2 in terms of v1 and v3, but we knew that at least one of those had to work. A homogeneous linear system AX equals 0 has only the trivial solution if and only if the column vectors of A are linearly independent. Here's why that's the case. So we know it always has a trivial solution, but if the only solution is the trivial solution, then the column vectors are linearly independent. Here's why. So if the only solution to this is the trivial solution, that's C1, C2, C3 all equals 0, well, we know we can write what I've circled as a matrix equation. 1, 2, 5, 2, 3, 9, 3, 4, 13 times the vector C1, C2, C3. So if this has a non-trivial solution, that means this is going to have a non-trivial solution. And that's why a homogeneous linear system AX equals 0 has only the trivial solution if and only if the column vectors are linearly independent. Because if these vectors are linearly independent, that means that the only solution to this is going to be the trivial solution, which means the only solution to this is going to be the trivial solution. Determine if these sets are linearly independent or linearly dependent. How about 1, 2, 3, 0, 0, 0? That would be linearly dependent. A set of vectors containing the 0 vector is automatically linearly dependent because you can express 0, 0, 0 as a linear combination of that. It's just 0 times 1, 2, 3. How about 1, 2, 3, 4, 5, 6? Yeah, that's linearly dependent. 2, 4, 6 can be expressed in terms of the other vector, 1, 2, 3. It's just twice 1, 2, 3. 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8. Is that set linearly independent? Is it linearly dependent? Oh, it's linearly dependent. A set of more than n vectors from Rn is linearly dependent. This is 4 three-dimensional vectors automatically dependent, linearly dependent. So we can add two statements to our invertible matrix theorem, that monster theorem that just keeps growing over the course of the semester. Let A be an n by n matrix. The following statements are equivalent. A is invertible. The column vectors of A are linearly independent. The row vectors of A are linearly independent. So again, if A is invertible if and only if this is true, and that's true if and only if this is true. Find the general solution of the system of linear equations and find a set of vectors which span the solution space. So again, we have this system of equations, looks like this. Here's our augmented matrix. And you know the routine. We want the reduced echelon form. Here it is. And now we express that using equations. So when we write the above matrix in terms of equations, we get x1 minus 4x3 minus 19x4 equals 0. x2 plus 4x3 plus 12x4 equals 0. Move the free variables x3 and x4 to the other side. And we get x1 equals 4x3 plus 19x4. And x2 equals negative 4x3 minus 12x4. So we can write them in this way. So we can write x1 and x2 in terms of the free variables x3 and x4. We know that x3 equals x3 and x4 equals x4. So if we separate those out, we can write x1, x2, x3, x4 in terms of this x3 vector and this x4 vector. Pulling out the x3 and x4, we see that you can express x1, x2, x3, x4 as this vector, 4, negative 4, 1, 0 times x3, plus this vector, 19, negative 12, 0, 1 times x4. Okay, so notice, this is a set of vectors which spans the solution space. 4, negative 4, 1, 0, 19, negative 12, 0, 1. Every solution is a linear combination of these two vectors. So we would say that these two vectors span the vector space. By the way, the CMYK model that we've been talking about is a subtractive model. You could use it for paint or ink or food dye. If you throw in a bunch of food dyes like yellow and red and blue, you'll get black. I know I've tried it. I've mixed them all together with the kids while making frosting. It makes this gross gray color. That would also work with paint and ink. However, light is an additive color model. So when you mix together green light and red light, you don't get this brown color. You get, wow, look at that. That's not what you'd expect the color to look like. And when you add together all of these lights, you end up with white. Again, not what you'd expect. You don't get black light when you throw all of those together because light is an additive color model.